we're ready to get started. Welcome everyone to the second day of the GEOS-Chem Europe users meeting. Before we get started, I'll just go through just a reminder of some of the etiquettes and best practices for the meeting. And then we'll move on to our keynote speaker, who is Volker Boersma, and then the rest of the science talks for the meeting. Just a reminder that the keynote speaker has 25 minutes to present with 5 minutes for questions. And then each speaker subsequent has 8 minutes to present and then 2 minutes for questions. I'll give you a 30-second warning to wrap up if you are at 7 minutes, 30 seconds for the science talks. And then I will manage the questions that appear in the Q&A box. So if you want to ask questions as attendees, please use the Q&A button that you should see available in the Zoom panel. And then I will manage those questions. And then for the panelists, if you want to ask questions, just use the chat box, as the Q&A feature probably doesn't work for you, as we've experienced from previous sessions. We've got a session for networking with the speakers after we're done. So the speakers will move into separate breakout rooms, and this is an opportunity for you to ask follow-up informal questions, introduce yourself to the speakers, just allow for some networking to take place in the absence of an in-person meeting. Can you progress to the next slide, please, Paul? Just so that you're reminded, I have sent an email this morning with updated day 2 poster session joining information. So that includes Zoom links as well as passcodes. Just a reminder that the webinar is being recorded. And then this is just something that we've noticed has been a little bit absent. Please ask questions of the speakers. This is your opportunity to engage with the speakers, push them on their science, contribute to the research that they're doing. We found that the Q&A was very quiet yesterday, so let's change that up today. We'll also be sending a brief anonymous Google form survey, and I know you're inundated with these, but we think that for this meeting, this is quite important because this might be a format that we have to adopt for the international GEOS-Chem meeting as well. So your feedback will be really valued for that. And again, enjoy, and we look forward to interacting with you during the meeting. And now I'll hand over to our keynote speaker, Volker Boersma. Thank you very much for joining us, Volker, and agreeing to give a presentation. We look forward to your talk.
Yeah. Thank you, my pleasure. All right, thanks, Paul, for putting the slides there. Okay, thank you for the opportunity to share with you what I think is a European story on air pollution. Actually is a lot of work done by my PhD student Marina Zara over the last year. And I must warn you that there will be not so much GEOS-Chem content in this talk. Actually, the degree of GEOS-Chem is very low, but I hope to make up for that with high content of satellite information and also some atmospheric chemistry. Now, on the right here, you see a TROPOMI map of the year 2019. And actually what you see is NO2 columns, indicated here as in Dutch as NO2 concentratie in milligrams of N per square meter. And what is really interesting here is that, that you can see a lot of detailed information on where NO2 pollution is actually very high in the Netherlands. And we see the usual suspects of Amsterdam. I hope you can see my mouse, which is here. And also the Rotterdam, The Hague area. Rotterdam, as you can see here clearly on this map, has a big harbor. But it's actually also interesting that we can now see sub-million inhabitant cities, such as Utrecht, which is close to where I live, and also Eindhoven here. 200,000 people live here. There's some industry surrounding that, and actually a satellite instrument can see this. Now you may wonder, okay, what does this have to do with trends between 2005 and 2018, when the TROPOMI instrument was not even flying? But one of the actual relevancies of this is that we have a big nitrogen crisis in the Netherlands. And this crisis is actually there because we have farmers causing a lot of problems. I already saw some hints in other talks that will focus on ammonia. And actually, here you see that in the west of the Netherlands, we have a lot of NOx emissions. Actually, in the eastern part of the country, we have a lot of ammonia emissions. And the farmers are actually clogging our highways on their way to The Hague to protest. And okay, I'm trying to, okay, here we go. Here you see this picture actually, that they pull up with their tractors to The Hague and protest and say, well, you want us to cut back on ammonia emissions. We don't want to do this. And they actually point at maps like these and say, well, look at this. The main industries in the Netherlands and also Schiphol, the airport, are polluting much more. So we're not going to do anything. Yeah, for that reason, it's important to tell these farmers what's actually going on in terms of NOx emissions. Do they have a point, those farmers? That's the question. Okay, well, according to the European Environmental Agency, the NOx emissions are reported to have been decreasing in the Netherlands and by approximately similar amounts. So the EEA reports a 38% reduction since 2005. And actually for the Netherlands, they report a 39% reduction. There's also a national inventory made by TNO that comes up with an estimate of 32% reduction. And by the way, ammonia emissions in comparison have not decreased at all in the Netherlands, according to these reports. Now, in spite of these reductions, the European Environmental Agency is also still reporting exceedances of European annual air quality standards across Europe and also in the Netherlands. This you can see by the red dots. You can see two tiny red dots here in Amsterdam and Rotterdam area, where the annual mean is still above 40 micrograms per cubic meter in Europe or in the Netherlands. Now, the official reports actually predict that the reductions in NOx are the result of higher standards for cars. So here you can see some of the standards I listed here. In the Euro 3 type of cars, there was an allowed emission of 0.15 grams per kilometer for NOx. And this has been tightened to, for instance, 0.06 gram per kilometers in the year 2014 when Euro 6 norms were introduced. At the same time, the industry has also taken a lot of measures, similar as in other continents. For instance, replacement of old coal-fired plants, replacement of coal by gas, etc. So, in principle, you would think that the emissions by cars and by industry should have indeed gone down. However, at the same time, we know that diesel cars that are much more polluting in terms of NOx have had an increasing share of the car market in Europe. You can see that here by this red line. This red part has grown drastically. So more and more diesel cars in Europe. And some companies have been less successful in actually implementing these Euro norms. And this has cast doubt on whether we have actually made those reported reductions. I know that the TNO and EMAP database account to some extent for the diesel scandal, but the question is how well do they account for that? Did they, for instance, take into account the cold starts of diesels or the influence of the outside temperature on the actual emission standards? Now, on top of that, there are changes in the economy. Economic activity has increased quite a bit in Europe. The question is also, how has that affected the NOx emission level? So, despite the reports, there's still many questions. Well, some estimates of NOx emissions suggest that actually not much has happened in Europe. So this is from a paper by Kazu Miyazaki that analyzed surface NOx emissions globally in the period 2005-2014 and used satellite data for that. And he shows that in Europe, there has actually been a 9% reduction per decade. That's the dashed light blue line that you see here. In Eastern Europe, there has been hardly a reduction at all. Well, if you contrast this to the US, it's clearly less successful in terms of NOx reductions from this estimate. And the question is this, then, okay, why is this? Has there been a change in chemical regime? Have there been change in lifetime of NO2? Has the diesel cheating been so pervasive that we hardly see any decrease? Now, at the same time, it's not just satellite data that suggests marginal reductions, but also the surface data. So this is from an EEA, European Environmental Agency report from a few years ago. And they show that the trends in NO2 annual mean concentrations observed at the surface are actually much lower than the reported reduction in NOx emissions. So the reported emissions in the period 2000 to 2014 were 44%, and approximately only half of that was seen in NO2 at the surface. Now, there may be many reasons for this, and one of the reasons is that the surface stations are often close to roadsides. And as reported in a paper by Grange a few years ago, there have been changes in the NO2 to NO emission ratio. So with the propagation of diesel in the market, more NO2 comes out of a car exhaust pipe, something like 15% in a few years ago compared to 5% in the early 2000s. And if the measurement station is really close to the roadside, it actually also measures that increase in NO2. So that is part of the story, and actually also an important reason in the remainder of this work why we have stayed away from roadside stations. Let's move on to to the research questions for this study that we try to address. Well, one of the main thing is, can we detect trends in OMI NO2 columns, and how do the trends relate to those in emission inventories, but also surface measurements of NO, NO2, and ozone, and in particular over the Netherlands. The data that we have been using in this study is from OMI QA for ECV. It's a data set we generated at KNMI and together with other institutes a few years ago. It's supposedly quite an improvement over the previous Domino product. We use also non-roadside EEA surface stations in the Netherlands. And we take a good look at the EEA and TNO MAC emission inventories and do some analysis with the mixed layer chemistry model class. Now, first, we take a look at the differences between tropospheric NO2 columns from OMI between 2 years. So these were the first and last complete year available to us when we started this study. And what we see here is obviously a large reduction in NO2 tropospheric columns over Europe. These data are, by the way, available from the QA for ECV website. And zooming in a little bit more on those differences, we see here the difference map between the 2 years. And we find that the reductions are actually strongest, about 40%, over those areas that are most polluted in 2005. So here we see that for really high columns, exceeding 10 to the 16th molecules per square centimeter, we actually find the strongest reductions. And what is also striking is that we see very little change between those two annual means over background areas. So that tells us something, that the free tropospheric background is probably not changing substantially between those years. Another striking thing is, of course, that the reductions in the Netherlands are really strong, and that has to do with the fact that we are a very polluted country, very dirty country, and also surrounded by very dirty France. Okay, let's now zoom in a little bit to the Netherlands. We see here the OMI columns averaged over 2005. So here you see the color bar for OMI, and overlaid we see the airbase or EEA surface concentration measurements with a similar color bar, but a different, but with different units, obviously. And if I click to the next slide, you can see how this changes in the Netherlands between 2005 and 2018. I will go back and forth a few times. You see that OMI NO2 columns reduce drastically throughout the country, and also that the surface airbase measurements change quite a bit. But note the different metrics. Now let's let's ask ourselves the question how the change was in time, and that is what we can see here. So here we no longer compare just 2005 to 2018, but we also see the interannual variability in the metrics. And what we see here is that OMI NO2 columns have decreased by 30%, but they show quite a bit of interannual variability. Surface NO2 has also decreased by a similar amount, about 32%, averaged over 23 stations in the Netherlands. What you can also see are the emission inventory showing a 32 to 39% decrease. From a trend analysis, we find that those the changes are statistically significant and are approximately 2.5% per year reduction. It's also striking that we see quite a bit of OMI interannual variability, much more so in OMI than in the surface data. We looked at that a little bit more in detail, and the main thing here is that it seems to be related to a lack of sampling in especially some winter seasons. So in some winter seasons we had very few data because of clouds, and then the means are less statistically meaningful. So that explains part of the stronger interannual variability in OMI than in the surface data. Moving on to making a separation in the country is what we did here, and this is basically to investigate if the reductions are stronger in the polluted south than in the clean north. So we drew a line from the Tata Steel engines here at the west coast, west of Amsterdam, all the way to Arnhem here on the east, and we called the north clean, which is of course a joke because there's lots of ammonia emissions there still, and we called the south the dirty south because that's where most people live and most of the industries and roads are. And what we found is that the OMI NO2 columns actually decrease less over the north than over the south. And this points in the direction of a hypothesis also put forward by some people from the Harvard group from the Silvern paper, that if you are in a situation where you have less surface pollution, then actually the role of the free tropospheric background staying constant becomes increasingly more important if you evolve through time. Now, this is something that we may actually see here in this difference between these two trends for the north and the south. As a reminder, the free tropospheric column is something like 0.5 to 1 times 10 to the 15, and the actual tropospheric columns are at least 10 times higher in the south, but in the north they're only 3 to 5 times higher. So that background could well start to play a role there. So that's important to take that into account when analyzing the satellite trends, as also put forward in the Silvern paper. Now we also looked at the surface trends, and now it becomes really interesting. The surface station seasonal means show that actually while NOx goes down, we see decreases in NO2 and NO, and at the same time an increase in the NO2 to NOx ratio. So especially in winter, we see that the reductions are much less pronounced in NO2 than in NO. In summer, there is a similar effect, but it is not as strong. And that points in the direction that a larger portion of NOx is actually NO2 in 2018 than it was in 2005. Now, this is important if we want to analyze the trends in NO2 from OMI in a proper way. So we looked a little bit further into this. And one of the things we did is we also looked at the co-observed ozone. So these measurements are all for 1 to 2, and we saw increases in ozone at the same time as the reductions in NOx. We saw a significant increase in winter and also an increase in summer, but this was from the trend analysis statistically insignificant. Now, this observed increase in ozone probably reflects the reduced NO titration by the reaction of ozone with NO, leading to NO2 and O2. So as NOx emissions go down, we have less ozone, and this will reduce the rate of the reaction shown here. And that can lead to a larger fraction of NOx staying at the right side of the reaction rate, in other words, in the NO2 form. Okay. Now we evaluated the meaning of this in two ways. We first looked at it via total ozone, where total ozone is defined as the observed ozone concentration plus NO2 in the Netherlands. And the idea here is that if total ozone stays constant, then the ozone increases are made up for by, or compensated for by, NO2 decreases. And we can say that, okay, there has been no net inflow of ozone into the area, and probably also no net photochemical production of ozone within the area. And indeed, in winter, we see that total ozone stays rather constant. So there is no trend at all, whereas there was a positive trend in ozone itself. And this suggests that the ozone increase that we saw over here in the Netherlands is exclusively due to the reduced titration from NO. In the summer, it is not as significant. There is still a hint that this effect is also there, but there is also still an ozone increase from other reasons than this reaction that I've shown. Now, we also investigated this hypothesis with a model, with a very simple boundary layer chemistry model. We did some idealized simulations for 2005 and 2018 in the southern Dutch boundary layer. This model simulates the diurnal cycle of weather, boundary layer growth, and also chemical species. And we nudged the model towards the observed values from the EEA stations at sunrise. And what I should also say is that there is simplified chemistry. There's 28 reaction rates in this model. Now, we first tested the model a little bit for its ability to capture winter to summer differences. And we found that indeed the model can reproduce the ratio between surface or boundary layer NO2 values. So RVM reports 3 times higher NO2 values at the surface in winter than in summer. And we can also simulate that with our class model if we nudge it and make sure that it also reproduces boundary layer depths that are typically observed over the Netherlands. So 600 meters in winter versus 1100 meters in summer. Same for the columns. OMI NO2 columns have a ratio of 1.5 to 1.7. That's smaller, of course, because this is now an integrated measure, and class also reproduces those ratios. So we have some confidence in the class ability to capture this, but again, this is in a highly idealized environment, nothing like GEOS-Chem. Now, then we interpreted the changes that we saw at the surface also with the class model, and we saw these similar reductions in NO and NO2 as observed in the model. So the model showed in winter a 56 and 27% reduction in NO and NO2. Our simulations show 41 and 29% reduction. The ozone increased by 20% as suggested by the observations, and in class we also came to a similar increase. And actually these model simulations with the chemistry, well-known chemistry that we know, also suggest this increase in the NO2 to NOx ratio in the dirty south of the Netherlands. Now, this has implications for satellite-derived trends, and then I'm almost at the end. So here we see again the winter NOx reductions over the Netherlands. We see reductions of 30%, but we think that if you account for the fact that more and more of the NOx has stayed in the form of NO2 in 2018 and in 2005, this should actually have represented a reduction of 34 to 41% in NOx, depending on whether you use the NO2 NOx ratio observed by airbase, or if you take the modeled NO2 to NOx ratio changes from class. So a stronger NOx reduction actually than what is indicated naively by OMI NO2 for winter. For summer, we see a similar thing, but not as strong. OMI indicates reductions in the south 38%, and we think they represent actually a slightly stronger reduction in NOx of something like a little bit more than 40%. So these are the implications for interpreting satellite data in a highly polluted country. Now, that brings me to the conclusions, which I will leave here for you to read. Bottom line is, we estimate that the wintertime reductions in OMI NO2 of 30% actually reflect a stronger reduction in NOx. And in summer, we don't see as strong an increase in the NO2 to NOx ratio because photolysis rates are much higher, and this makes for faster conversion of NO2 to NO, of course. But we still estimate the NOx reduction to be a little bit higher than that of NO2. Now, as a point of discussion, we may wonder if we can also say something about the actual changes in emissions. And that is a little bit more difficult at this stage. We did not account for instance, in the modeling for year-to-year changes in meteorology. And actually in the model, we did not drive the changes just by emissions, but also by prescribed initial conditions that we got from the observations. So from that, it is very difficult to say, okay, emissions have reduced by this amount or by any other amount. There are some possible implications for NO2 lifetime, but I think in interest of the time, I will leave it at this. I think I don't want to go over my time, and that may have happened already. So with that, I'd like to conclude and happy to take the questions.
Thanks, Volker. You were perfectly on time. I'm just going to encourage people to put any questions that they might have in the Q&A box. In the meantime, I will ask a question related to the ozone increase, which looks really interesting for summer because it's now at the cusp of this 40 ppb sensitivity for crops. Has anyone started looking at whether there is an implication for the kinds of crops that are grown in the Netherlands? You know, are we increasing sensitivity to food security?
Yeah, this actually comes a little bit back to also what Nadine has been showing yesterday. And that was actually, I was very happy with one of her slides where she showed that if you halve emissions, then you can gain a lot in terms of ozone exposure to crops. So basically her point was, okay, if we halve emissions globally, we get a lot of more CO2 uptake and crop yield. But actually what you also showed is that this is not at all the case in the Netherlands. Half emissions, we only get more ozone, and that's exactly in line with what we see in this study. Although most of the ozone increase we saw over the last 13 years was in winter, or most clear. Yeah, so I'm also supervising a PhD student who is investigating the way to best calculate ozone exposure to vegetation, and he's very much into looking how we can use more detailed models of canopy and lower atmosphere exchange to improve that. So basically taking a little bit step away from the Weasley scheme, the big leaf area, the big leaf approach, and but he's focusing really on a small scale and not taking a global approach and estimating the exposure as such already. I hope that answers your question.
I see we have a quick, yeah, it's complex. Yeah, and I see we have a question from Rob Ryan as well. He says, thanks for the nice talk. And he was curious whether there's a difference in how the NOx long-term trend is over the Netherlands between the weekend and the weekdays, and whether this might help in interpreting the contribution of traffic to changing NOx emissions. Yeah,
that's an excellent point. We haven't looked at that. But that may well be the case. So in the weekends, indeed, the NO2 levels are something like 50% lower. So it would be interesting to tease that out, but we haven't done that yet. So, but it's a good point. It's something to check out.
And I suppose as a final question, in terms of regulating NOx, is it entirely up to the manufacturers, or is there any kind of NOx test for cars on an annual basis in the Netherlands, maybe better than the UK does.
Well, I don't know what is being done in the UK, but I know, so we work together with the people from TNO. They're also close to KNMI here in Utrecht, and they regularly go out and do specific tests on the actual driving conditions of the cars. So this whole diesel scandal was actually already known by them, they claim. They didn't put it into the press, but they knew already before the whole diesel scandal came out that certain types of cars were polluting much more or emitting much more NOx than was reported officially. And they also put this in their emission inventories, they claim. So yeah, I don't know how different it is in the UK, but there are quite frequent tests. Question is, of course, always how it will be dealt with and implemented with by the European laws.
Okay, thanks, Volkert. In the interest of time, we should move on. Thanks for a really great talk.
Yeah, thank you.
Our next speaker is Yuhan Zhang. Thanks.
Okay. How can I get to the first page? Maybe it's I have nothing, no reaction here.
Yeah, just make sure you click on the screen and then it should activate your control and then you should be able to progress. There will be a slight delay though.
Yeah. Okay, now everything's fine. Okay, I'll start. Hello everyone, I'm Yuhan Zhang from Peking University. And here I'd like to talk about the differences of NO2 spatial temporal variabilities in summer between multiple satellite products. As we all know, model simulations and satellite retrievals are closely connected. Chemistry transport models can provide us with huge amounts of information, including state parameters like pressure and temperature, and spatial temporal distributions of specific species. And the satellite retrievals will use this data as inputs, together with other ancillary parameters to do radiative transfer calculation, and finally get vertical column densities. So, based on that principle, we use data from GEOS-Chem simulations and other official data sets. We developed the POMINO algorithm to retrieve tropospheric NO2 VCDs. One point that needs to be emphasized is that compared with other retrieval algorithms, POMINO makes explicit aerosol correction in the cloud and the AMF calculation, which makes the results more accurate in China. And since this part and this chart, this diagram is too technical, so maybe we can come back later if necessary. Okay. This GIF on the left in this slide shows us the spatial variabilities of tropospheric NO2 VCDs in China in July from 2015 to 2019. We can see high value regions are mostly in northeast China, marked with this red rectangle. This is because the lifetime of NO2 is relatively shorter in summer, and most heavy industries and other emission sources are located in this area. Besides, we can clearly recognize three major metropolitan areas in China. They are Beijing, Tianjin, Hebei province, Yangtze River Delta, and the Pearl River Delta. And the line chart of the average tropospheric NO2 VCDs in northeast China is shown on the right. In this chart, we can clearly see a non-monotonic decline trend in this area. And this partly results from the emission control and air pollution management in China since 2012. But also we can see a flattening trend beginning from 2006, like here. And this may, I believe, may reflect some other natural factors of NO2 that are irrelevant to the government management, like atmospheric transporting and complex chemistry mechanisms. And of course, other than POMINO, oh, wait a minute. Okay, and of course, other than POMINO, official QA for ECV is also well, oh, sorry. Yeah, other than POMINO, official QA for ECV data is also well known and widely used. So this panel compares the spatial variabilities of tropospheric NO2 VCDs in the same time series between POMINO and QA. In the first two charts, we can see generally these two products are very similar in spatial distribution. Both of them consistently present the high value regions in northeast China, and we can clearly see the major metropolitan areas. But if we see the third figure, the relative difference of POMINO to QA, we can find that POMINO results are consistently higher than QA in some certain regions, like Yangtze River Delta. So I think this can be attributed to the difference of retrieval algorithms, including the different models, different ways of calculation, and different treatments to some certain parameters. And this, sorry, some delay. Okay, and these two charts shows the similarity and the difference between POMINO and QA more obviously. The left line chart of the average tropospheric NO2 VCD in northeast China shows a decline and a flattening trend in both two products, although there are some obvious difference. And combined with the right bar chart of their relative difference, we can see that the difference between POMINO and QA are getting much smaller after 2015. I think this also demonstrates that the emission and the environmental change in China in these years, and also the characteristics of each algorithm. And finally, okay, and finally, to understand the effects of aerosol correction and the surface reflectance on the difference between POMINO and QA, we conducted 3 sensitivity tests based on POMINO algorithm. The time we choose is the July 2017 because we got similar results in other years. So these two panels shows the relative difference of test results to POMINO and to QA. In the first panel, we can say using either implicit aerosol correction or LER surface albedo can result in at least nearly 5% change relative to POMINO in northeast China, and their combination effect can reach to 11%. And in the second panel, we can see the combination effect case is only 0.45% lower than QA. And I believe this, the aerosol correction and the surface reflectance are dominant factors in the difference of between POMINO and QA, at least in this time and in this area. So in the end, sorry. Okay, sorry. So in the end, there are my 4 primary conclusions. The firstly is high-value regions are mostly in northeast China and the Pure River Delta, both in both products. And secondly, despite obvious difference, both products show a non-monotonic decline trend and a flattening trend in summer from 2015 to 2019. And thirdly, I think the most important, the spatial temporal variabilities partly reflects the results of emission controls and air pollution management in China, but the flattening trend implies many other contributions to VCDs. And finally, the last point is different treatments of aerosol optical effects and surface reflectance can play a significant role in the difference between 2 satellite products. Okay, that's all my presentation. Thank you very much.
Thank you, Johan. We have a question from Fulcrit. Has there been an observed decrease in AOD from 2015 to 2019 that could explain the convergence between the QA for ECV and POMINO products?
Oh, sorry, I haven't checked the AOD change. So maybe I'll check it later. But I only saw the NO2 trend.
Could you speculate that if AOD is decreasing over China due to air quality policies, what the implication would be for the POMINO product compared to QA for ECV?
Maybe so speculates the AOD.
Yeah. So what would be, what would be the implication on the product for a change in AOD?
Oh, I mean, in China, I think it's a little complicated because we will both check AOD and SSA of aerosol properties, and right now I haven't checked these properties, so maybe I'll check it later.
Okay. Great, thank you, Johan. Oh, Volker, did you want to follow up?
Yeah, can I say something about that? So Yintai actually also answered in the chat that this could indeed be one of the reasons why the algorithms become closer. And I know that in any case, the KNMI algorithms, they have difficulty if aerosol loading is really high. Then the cloud algorithms basically report wrong cloud pressures, and this may play a role. If if AOD is lower, then the implicit correction that we do for aerosols via the effective cloud fraction is actually working quite well, as we shown before.
Yeah.
So we might be in the lucky circumstance that AOD is getting now China and the algorithm to behave better. It's a hypothesis.
Thanks, Volker. In the interest of time, we should move on. Our next speaker is Jintai Lin, and I suppose he will elaborate on a little bit more on the aerosol correction that's being applied. Over to you, Jintai. Just a reminder that there is a slight delay when you progress the slide. Jintai, you're on mute.
Okay. Thank you for the opportunity to be here. I'm going to talk about our new TROPOMI product, which is based on our previous POMINO algorithm that my student Yihan Zhang just mentioned. Okay, oops. Of course, you can see this pretty good picture, pretty kind of nice picture for the global NO2 tropospheric NO2 vertical column densities. That's from the KNMI group, and you can also see very high hotspot for NO2 because of the short lifetime of it. And of course, over Eastern China, you still see the highest NO2 level among the world countries. So, the next question would be that how do we calculate the NO2 column from the satellite observed radiation? And basically, well, we are able to do so because the absorption and scattering feature of constituents, including molecules, including air molecules and particles, and even the ground, it's very distinctive features in the fitting window of the trace gas of interest. And in this case, NO2. For example, you can see that over this region, you have very distinctive optical depth of NO2 that's in a very high frequency way with the wavelength. And this feature is very different, of course, from other absorbers and aerosols. So using this kind of information, one could use so-called DOAS technology to calculate the standard column density of NO2 based on its cross-section. And so And because the sand column density is measured along the average path of light from the sun from the sun into the atmosphere, reflected back to be observed by the satellite. So what we are interested, of course, is not the sand column density itself, but the tropospheric vertical column density. So the way we calculate from SCD to tropospheric VCD is to remove first the stratospheric influence, which of course would introduce some uncertainty in addition to the DOAS technique, which introduced the first uncertainty for our estimate of tropospheric NO2 vertical column density. But of course, especially over the polluted area, is coming from the calculation of so-called air mass factor. And this is how our algorithm come in. And basically, this on the left side is the details in the official algorithm by KNMI. And of course, implicit aerosol correction, which basically means that there's no explicit aerosol information in the whole algorithm. So aerosol is treated as effective clouds, some sort of effective clouds. And also, they don't consider the geometric dependence of surface reflectance. Of course, they are using relatively coarse horizontal resolution to provide NO2 file. And this is important because we need to use the vertical shape of NO2 to help retrieve to help calculate the MS factor. And as I will show you later, this turned out to be very important as well. And so basically, our algorithm is largely based on an inclusion of aerosol information that's coming from GEOS-Chem Classic, of course, adjusted by satellite measurement of AOD. And we also have higher resolution NO2 profile that is also from GCC. And also we have considered the surface, the geometric dependence of surface reflectance. And this is the whole algorithm flow chart, which I'm not going to go into detail. Instead, I'm going to show you the result here. So our algorithm for TROPOMI covers the whole China and parts of East Asia and South Asia and Southeast Asia. And by comparison, this is our product and this is the official product from KNMI. And as you can see, on a large scale, they are very, very similar. Okay, if you calculate the correlation, the spatial correlation would be like 0.95. So it's great. But if you look into a little bit detail, especially when you look into the hotspots, then you will see that our algorithm shows a lot of hotspots that's not very clearly shown in the official product. And if we zoom into, say, Beijing here, and Beijing, by the way, is the capital of China. And so you can see very, very large hotspot in our algorithm, which is much less strong in the official product. And we can also see some small features like this small dot, which we are related to the kind of urban development, which are also not very clearly shown in the official product. So, and we do try our best to try to evaluate the two products using the amount of three size of max DOAS measurements over China and Japan. And we have clean, we have intermediate, and we have also very polluted cases combined. And you can see that our algorithm produces a relatively good correlation and small bias as compared to the max DOAS measurements. And by comparison, the official product show a very large negative bias, basically an large underestimate over China. And our results actually consistent with the result from other groups that just published in this year in, I think, AMT as well. Okay, so basically globally, this official product have some kind of bias about 30% or so, with a range of maybe 20 to 50. And in our case for China, it's about 40. And we look into what's driving these differences between the products, of course. And the first thing we look at is the effect of implicit versus our explicit aerosol treatment. As you can see that for July 2018, you can see over the polluted areas of Eastern China, there's large difference there's a large negative value from explicit to implicit. Basically, our explicit aerosol have higher value than the implicit aerosol.
30 seconds.
Okay. If you look at the effect of resolution, you can see if you use a low resolution NO2 profile, you can produce a very large bias over the coastal oceans. And that's because the profile cannot show the correct vertical distribution of NO2. Okay. So, okay. It's now moving. Okay, I'm going to skip this and to stop here for the time being and take questions. Thank you.
Yeah, if you have
by
any
the way,
questions.
Yeah.
Yes.
Yeah. Sorry. By the way, our product is going to be publicly available in about 1 week or 2 weeks. Okay. You're very welcome to use them.
Thank you, Jintai. I see we have a question from Volkert, but I'm going to ask you to step in and ask it, if that's okay.
Yeah, sure.
Yeah, it's actually it's not a question. It's more a comment. Excellent presentation, Jintai. We are well aware of at KNMI of the improvements that need to be made, and some of those are already underway. One thing that is difficult for us is to improve on the TM5 spatial resolution, because this is just available to us at 1 by 1, and there's no plan soon to improve on that spatial resolution. But what you see throughout the world is that many groups have been using their own a priori profile shapes at high resolution. So Jintai has done that in Beijing. Other groups have done this in Finland, in Belgium, and also in Canada, I know. And actually what Danielle showed yesterday is the availability of super high resolution NO2 profile shapes calculated by Matt's group. These could also be plugged into the air mass vector calculation of TROPOMI for global retrieval. So yeah, we could hopefully there would be some energy to set up a project like that and improve on the spatial resolution of those profile shapes.
Yeah, I totally agree. And one of our projects in my group is to produce global high resolution simulations, like 25 kilometer. And one of the targets will be to provide this high resolution NO2 profile for satellite retrieval. Yeah, we could talk later much more.
I have another question from Rob Ryan. He's asking whether the NO2 a priori profile shape is allowed to vary in the retrieval or whether it's held fixed.
I think it varies spatially and temporally. It's daily data, and I think it's early afternoon data which match the overpass time of any satellite data, and it's of course spatially varying.
Great, thanks, Jintai. Our next speaker is Maggie Marvin.
Hello, just a thing, okay. All right, hi everybody, I'm Maggie Marvin and I'm from the University of Edinburgh, and I'll be talking about the impacts of biomass burning on air quality in Southeast Asia. And I'll be focusing on both ozone and PM2.5. So biomass burning is extremely common in Southeast Asia. Fires are often started intentionally to clear land or for agricultural purposes. And so we'll be looking at biomass burning specifically for 2014, which was a moderate burning year. And so the plot on the left shows a time series of biomass burning emissions from 2014 from month to month. And then the plots on the right show the spatial distribution. And when we consider both together, we find that there are two distinct burning seasons in Southeast Asia. So the first one peaks in March and occurs over mainland Southeast Asia. And then the second burning season peaks in September and occurs across Indonesia. So to study the role of biomass burning and its impacts on ozone and PM2.5, we use GEOS-Chem. And we run GEOS-Chem in nested mode at the 1/4 degree resolution. We use full gas and aerosol chemistry, specifically the complex SOA-SVPOA mechanism. We run the model with biogenic emissions from Megan, run online. We use anthropogenic emissions from SEDS, and we supplement with Asian emissions from MIX. And then for biomass burning emissions, we use GFED 4.1S. And so to evaluate the model, we use a couple of different observation data sets. So we use tropospheric ozone profiles from OMI, AOD from MODIS, and then we surface observations from Southeast Asia are very, very sparse. But we do have some surface observations of ozone provided to us by the Malaysian Department of the Environment, and so I'll be showing that as well. Okay. So here we are showing model simulated ozone and PM2.5 from March and September of 2014. So these are monthly means, and the units are relevant to national and global exposure guidelines. So for example, the World Health Organization recommends that MD8 ozone, which is the unit we use here, so maximum daily 8-hour mean ozone, should not exceed 100 micrograms per meter cubed, which is about equivalent to 50 ppb. And for PM2.5, the exposure guideline is provided for the 24-hour mean and should not exceed 25 micrograms per meter cubed. But when we look at the model results, we see that the model predicts that both ozone and PM2.5 exceed these exposure guidelines, in some cases pretty significantly, for a prolonged period of time over a large area of our domain. And this could put many lives at risk. So to try to understand the role of biomass burning in the formation of ozone and PM2.5, we look to some of the precursor species. So for example, NOx and VOCs. And so here we're showing emissions of NOx and non-methane VOCs month to month from 2014. And these are separated by the source sector of the emissions. So for NOx, we see that the emissions are dominated by the anthropogenic sector, but the seasonal variation is driven very significantly by the biomass burning emissions. Whereas for VOCs, both the magnitude and the variation are driven pretty strongly by the biogenic sector, although there's some contributions also from biomass burning. So to estimate the impact of biomass burning on ozone formation, we use what's called the ozone formation potential, which we calculate directly from speciated VOC emissions. And so what we do is we multiply those VOC emissions by what's called a maximum incremental reactivity factor. And these are specific to each VOC. And they represent the reactivity of each VOC and the probability that once that VOC reacts, it will go on to produce ozone. And so the table here lists some of the VOCs that contribute the most to OFP in Southeast Asia. And so at the top of the list is isoprene. And so when we look at OFP, so the chart or the plot here on the right, that shows OFP separated by the different source sectors. And so the biogenic sector, shown in the green, totally dominates. And so the contribution from pyrogenic VOCs is actually very small, maybe 10 to 13%. But when we consider the overlap between biogenic VOCs with pyrogenic NOx, the total pyrogenic contribution to ozone formation potential increases to about 30%, which is much more substantial. Okay, so PM2.5 is a bit of a different story. So NOx and VOCs contribute to individual components like SOA, but some of the larger components in Southeast Asia in March and September are POA and oxygenated POA. And we find that both of these are attributed mainly to biomass burning in Southeast Asia during this time. And that overall, we estimate that biomass burning contributes about 40% to total PM 2.5 in March and September, or up to 40%. All right. And so we evaluate our model results against satellite observations. So for both ozone and aerosol optical depth, and so those are both shown here. In both cases, the model is shown by the black bars, and then the satellite observations are shown with the gray. For OMI ozone, that hatching above it just represents a systematic error range that we suspect might be impacting OMI ozone based on a comparison to ozone zones. But when we look at both ozone and aerosol optical depth, we see that the model seems to underestimate the observations in some cases pretty significantly. So this could suggest that exposure to ozone and PM 2.5 could be worse than indicated by GEOS-Chem. But of course, the satellite observations don't necessarily represent what's going on at the surface. And so when we look at our surface observations that we have from Malaysia, so this is not the case and it doesn't agree with the satellite comparison. So we see that when we compare to the surface observations, the model actually agrees pretty well and may in fact overestimate, which is different from the comparison that we got with the satellite. And so this discrepancy is interesting, but difficult to interpret without having more surface observations to be able to compare against, but it's definitely worthy of further investigation. Great. And so major conclusions are that we find that there are two distinct biomass burning seasons in Southeast Asia. And both of those can contribute to the production of ozone and PM 2.5. We find that biomass burning accounts for about 30 to 40% of regional ozone formation potential and PM 2.5 in March and September, respectively. And then we see when we compare to the satellite observations that exposure could potentially be worse. But with the surface observations that we have at the moment, there's no confirmation of that yet. So yes, I'll end there and I'm happy to take questions.
Great. Thanks, Maggie. We have a question from Amir, and he's asking whether you've run any sensitivity tests with GEOS-Chem in terms of plume rise parameterization, where the current assumption made in the model is that 60% of the biomass burning emissions within the PBL or planetary boundary layer are uniformly distributed. And this may not always be the case.
Yeah, no, we haven't done that, but that's something that we've thought about and could definitely be impacting the differences between the surface and the tropospheric observations. So definitely something that we could look at.
Okay. And I suppose in a similar vein, have you tested or at least examined whether you're underestimating the oxygenated VOCs from biomass burning and how this might influence the ozone production efficiencies that you've calculated?
No, we haven't looked at that either, but definitely something that we could take into account.
Okay, great. Thank you very much.
Mm-hmm. Thank you.
Our next speaker is Xiaonan Wang.
Okay, oh, sorry. I can't find the screen. Okay. I send the remote control. Okay, I'm Xiaolin Wang from Peking University. Today my topic is about the trends of surface and tropospheric ozone over Southeast Asia and their drivers during 25 to 2040.
Sheldon, we're finding it hard to hear you. If you're using a mic, can you just lean into it a little bit more?
Oh, can you hear me? Hello?
Yeah, unfortunately, your sound isn't very clear. We're going to have to move on to the next speaker. I'm not sure if you can address it just by doing a sound test between now and the end of the session, and we'll come back to you.
Oh, okay.
Thank you. So Amir, if you're ready, we'll move on to your presentation.
Okay.
Thanks.
Hello, everyone. This is Amir Suri from Harvard Smithsonian, and my today talk is basically designed to bring up a overlook error when it comes to using formaldehyde to NO2 ratio in order to pinpoint chemical condition regimes. And also I will show some very first results of the chemical condition using geotazo airborne observation, which is pretty, has a very high resolution, and you can see how the chemical condition change throughout the day. So when it comes to ozone production, we know that it's a nonlinear function of VOC and NOx. And because we don't have all the observation to basically understand the relationship, we resort to using some sort of indicators, for example, H2O2 to nitric acid or H2O2 NOZ. So basically they drop some hints on whether we are in NOx sensitive or NOx saturated and how that first approximation of that nonlinear relation look like. Seelman, several years ago, 18 years ago, he found that if you look at the H2O2 to nitric acid, you can get a very good estimate of that regime, which makes it the best proxy for that chemical condition. And it makes sense because nitric acid is a primary product of NO2, whereas where you have in rural setting, when you have all the radical branching and H2O2 reaction, usually you have higher H2O2, which this ratio is highly correlated with the loss of ROx to loss of NOx, which completely explain the ROx cycle. This is the best indicator, but the problem is that we don't have a good observation from satellites. So they're only limited to some scarce limb sounding with limited sensitivity to PPL. We know that the formaldehyde NO2 retrieval have been very successful from remote sensing. Ironically, using this ratio never endorsed from chemical point of view. So the reason that people are interested in using it is because of the accessibility from the satellites. A lot of people use that ratio. I use it too, to see the spatial distribution, the long-term trend, like more toward qualitative analysis. But when it comes to quantitative, we know that we need to know a lot of parameters. We need to know the retrieval error. We need to know the relationship between the PBL, or we say ground level, and the column. But we want to say it in this study, even if it was perfect, if you don't have any retrieval error, and if there is a perfect relationship between column and surface, you still need to define different threshold when it comes to pinpointing those chemical conditions because of the NO2 and formaldehyde chemical feedback. In order to prove that hypothesis, I ran an ensemble of box models using DC8 observation during course AQ in 2016. I'm not going through the detail, but that's this is the observation I use in order to constrain the box model to get ozone production rate, VOC reactivity, and do some sensitivity tests. The time period that I'm going to focus is June 9th, 2016. You can see this is the ozone the left and right side surface ozone from the CMAC model we ran, you see that the isobars over Seoul or Korea is expanding. I mean, that's the indication of the stagnant condition. And the background value is going up. So all of them go hand in hand and result in very high ozone concentration during stay. So it's interesting because the air quality is very degraded. So here, at June 9th, 2 to 4 p.m., we retrieve NO2 and formaldehyde from geotest observation. NO2 is done by Luck Lamson and formaldehyde by Caroline. And the contour map and the background is the geotest observation, which is a sensor very similar to the Flowchart and TROPOMI, but with high resolution. It's 250 times 250 square meter. And I overplotted the DCE measurement. As you see, there's a huge, I would say, strong degree of correlation between those observations between DCE and geoteso, which is not only indication of a very good retrieval, but also the fact that the boundary condition is well mixed. The PBA is 3.4 kilometer. So those points from aircraft is a very good representative of the column. You see the formatta is pretty high, close to Seoul, here, this area. You also see a high VOC reactivity too. And the reason for that is that because there's a park there called Olympic Park. You have a lot of isoprene right in the city when you can see it from both this observation. So that resulted in a huge amount of VOC reactivity, which eventually will result in large amount of ozone production because it's in a NOx-saturated regime. But back to our problem, the first assumption people made in terms of using the formatta NO2 ratio is that they say formatta is a good proxy of VOC reactivity. We have VOC reactivity and DCA formaldehyde follows a logarithmic ratio, which means that it's not true, especially in VOC-rich environment. The correlation between these two is pretty low because you have more variables. You have aromatic VOC. You have is not necessarily follows the formatta does not follow exactly those reactivity values. And in low values also, sometimes you don't have that very good correlation too. But in normal situation, we can fairly say that's a good assumption. So we have problem in both rich and poor environments. Just a very simple analysis between ozone production and the NO. So you see that is linear in rural area because you're NOx density and becomes quadratic when you're looking at the rural urban areas because it's saturated air regimes. But the main part of my study is this contour plot. So you have bipertab NO2 and formaldehyde, and you can see the background, the contours are ozone production. You have the ratios of 1, 2, and 3, and these purple lines is L NOx to L ROX ratio, which is the best indicator to differentiate NOx saturated from NOx sensitive regimes. You can see 2.7 actually is a line. If you follow this line, then you would need to define the formaldehyde to NO2 ratio from 0.1, 0.5, 0.5, or 2, and then like 3 and then 4. So you need to give a lot of recipes to people to basically differentiate this. And there's usually the discrepancy between this, the transitional line and this formaldehyde to NO2 equal 1, which commonly people use, is huge in this area and this area, in very VOC-rich environment and poor area. And this is because the fact of production of formaldehyde depends on NOx. And we know that in VOC poor area, when you increase NOx, you have a reduction in the formaldehyde production, and in the VOC-rich, you have an enhancement because you increase OH and VOC oxidation. So you have a feedback from a denominator on numerator. And that's a result. For example, here, at this part, if you see, if you increase NO2, you decrease the formaldehyde production. So if you increase NOx, you basically go toward this path, which means this area was in oxide regime, which wasn't captured well with the commonly used thresholds, all because of this chemical feedback, and is opposite in the other part of the contour. So we see that the chemical feedback between NO2 and formaldehyde can basically add a different layer of complexity when it comes to using this ratio. So instead of giving people a lot of thresholds, okay, in this environment, please use this ratio, we just can reformulate this formula to a line that match with that L-NOx to L-ROX ratio, which considers the chemical feedback. So we can provide this line that if you're on the right side of is NOx saturated and left NOx sensitive, and you only give 2 numbers to people, then this line doesn't have the complexity that result of that chemical feedback. So using that ratio, that line, we classify the chemical condition over cell at different time of the day. Because that geotasa I mentioned, it overpasses different time of day, and they wanted to use it as a test bed for tempo. So over the 10 to 12 local time, we expect that because of the less active photochemistry and higher traffic, you have more higher NOx than formaldehyde. Then you would expect higher NOx saturated regime, which is true, is stronger here. And as time goes, it shrinks or become less stronger. And you can see the place that we have a lot of ozone production rate is a place that you have NOx saturated and there is a park there. So you see this subtle variability that you can see from the satellites.
Amir, are you about ready to wrap up?
Yeah, so just to want to say that we found that, okay, L-NOx to L-ROX ratio is a good indicator. If you follow that, you need to give a lot of thresholds. So instead of doing that, we can basically reformulate the formula to a line that consider the chemical feedback. And with that, we're using geotasa, we found a very interesting variability associated with the chemical condition over cell, which is not observable with satellite remote sensing. Thank you.
Thanks, Amir. We'll take one quick question. And this one's from Matt. How sensitive are you to the chemical mechanism you've used? For example, carbon bond makes a number of assumptions about the chemical mechanism. Do you think your conclusions are robust to that?
I would say that the fact that NO2 impacts the formaldehyde formation is basic enough that you can, when I changed some of the chemical condition, I changed to CBO6 and GEOS-Chem, and I did some MCM analysis, even though those were very slow. I still see that trend. The values may change, the yield may change depending on the complexity, but it doesn't change the conclusion from this study.
Thanks, Amir. We'll move on to Alok, and then we'll come back to Shaolin after Alok. And hopefully, if your sound is working, your presentation will proceed. If it isn't, we'll close up the session. Over to you, Alok.
Hello, everyone. I'm Alok. I'm going to present about UK ammonia emission derived with ERC satellite and GEOS-Chem climate transport model. So ammonia gaseous ammonia is the most abundant alkaline gas in the atmosphere. And the largest source of gaseous ammonia is agriculture, including animal husbandry and ammonium-based fertilizer applications. Gaseous ammonia reacts with VOC, NOx, SO2, and creates ammonium salt, which is one of the major constituents of the particulate matter 2.5, and which is directly going to impact human health and have climate impacts as well. So gaseous ammonia impact on the UK is, I'm unable to move it. Oh yeah. So in the left figure, I'm showing UK NAEI ammonia emissions, and you can see ammonia emissions is distributed around whole UK, and over Northern Ireland it is more. The main cause of this increase is due to the Northern Ireland is responsible for around 12% of UK ammonia emissions, despite having only 3% of the populations and hardly 6% of agriculture area or land area. In the right side, you can see the changes in the ammonia and different PM2.5 precursors and PM2.5 and 10 as well. So 1970 is the index for others. For ammonia, it is 1980. So you can see clearly that all precursors are changing rapidly since 1980s onward or 1920s onwards, but there is not huge change in the ammonia emissions. So in 1980s, it was hardly 320 or 330 gigagrams. Now it is around 270 gigagrams. So there's not huge change in that. Reported uncertainty in ammonia emissions is 20%. So why this is more important? Because ammonia emitted after fertilizer application, and it has wet depositions if it is in the atmosphere, and when it reacts with the different gases, it is going to impact its lifetime increases further to 1 to 3 days, and after precipitation experiences, it's deposited on the ground. So it has impacts. The chemical process and physical process are very complex, and it's very challenging to derive ammonia emissions using standard approaches. So what I'm doing in this current project is I'm trying to compute ammonia emission using ERC satellite columnar data of ammonia. So I'm using awareness of that. I'm running GEOS-Chem CTM model. The version is 12.100, and I'm using the conversion factor to compute ammonia. The emissions we have used is the GEOS-Chem is updated with the national NAI emission for UK and EMAP emissions from the Europe. And further, we compute ammonia emissions, and this is satellite-derived ammonia. So in the next slide, I'm evaluating it with the GEOS-Chem using DEFRA. So this is the Department of Environment, Food and Rural Affairs network data. So this is well distributed over whole UK, and you can see why it is changing. I'm able to control it. Can you go to previous slide? So oops. So
there is just a slight delay. So once you progress, you do have to wait a bit. Or Paul, if you want to take over and just be prompted by Alok on when to.
Yeah, please, when I'm pressing, it's not changing quickly. Anyway, so for ammonia, the model is 50% lower, and the slide 5. Yeah. So for ammonia, so I have the circles are the observational data, and the background is the model. So we can see here ammonia is 50% lower than the observations. For ammonium, it is the model hardly differs for 10% in the annual means, and these are the annual means. So this is, but there is a seasonal differences in the model and observations. So NHX is due to large underestimate, model underestimates NHX due to large underestimates in the ammonia. So there are some differences, and there are seasonality in this data, but more or less ammonia is underestimated by more than 50%. Next slide, please. So I further evaluated this for HNO3, nitrate, and sulfate. For sulfate, model is doing right, but for HNO3, model is overestimating by more than 1400%. So this is because HNO3 in the observation is too low, and model is doing a little higher. So this is a lot increase in HNO3. Nitrate, this is underestimating, and this is mainly due to the, I suspect the large underestimate in the nitrate is because of underestimating ammonia in the UK and mainland Europe. Sulfate is doing good. Next slide, please. Yeah, so here I am comparing GEOS-Chem column concentration of ammonia and ERC column concentrations. So you can see clearly, visually, you can clearly see that ammonia concentration in the GEOS-Chem is 70% lower than the ERC column concentration, which is also reflected in the scatter plot, which I'm showing in the right panel. And the blue line is one-to-one line. So you can visually see there are more ERC column concentration towards upper panels, and correlation is really good. So it is correlated well, but model is 70% less estimating, and or you can say other way, the satellite is data is more. So it is supporting the low bias in the NAI emissions. Next slide, please. So in a nutshell, I can say GEOS-Chem, the model is biased low compared to both the surface and satellite column observation. That the model does a poor job in the producing the aerosol nitrate concentration, and this may be due to the error in the ammonia emission in the UK NAI and Europe EMM. That the implication is underestimating ammonia emission is an underestimate in the two important PM2.5 component for the UK. The work is in the progress, and the next step is to evaluate UK national emission with the ERC-derived ammonia emission. Thank you. Happy to take any further question.
Thanks, Alok. We have a question from Jintai. He's asking how large the error is in the ERZ ammonia columns over the UK.
So I have not checked the error in the ERC one. There is definitely some, when you see the spatial plot, there is some noises in that, but I don't have the exact figure of error in the ERC column concentration.
Thanks, Alok. In the interest of time, we'll move on to Shaolin.
Okay, can you hear me now?
Shaolin, are you there?
Yeah, can you hear me now?
Yeah, you'll have to speak up a lot though. You're coming across quite soft.
Oh, okay, I will speak louder.
Thank you.
Today, my topic is about the trends of surface and tropospheric ozone over Southeast Asia and their drivers during 2005 to 2014. Over the Southeast Asia region, the rapid economic and population growth increasing the demand for energy, which can produce an increase in certain air pollutants such as NOx and ozone to the atmosphere. Several studies have reported tropospheric ozone increase over Southeast Asia based on aircraft, ozone sound, and satellite data set. And the equatorial displacement of the anthropogenic pollutant since the 1980s may have caused the largest lower tropospheric ozone increase in the tropics, especially in South and Southeast Asia. So in this study, we try to present an integrated analysis with measurement from multiple platforms and the GEOS-Chem model with the goal of quantifying the trend of seasonal surface and tropospheric ozone and their drivers over the Southeast Asia during 25 to 2014. Here, the Southeast Asia region in our study, including the peninsular Southeast Asia and the maritime continent. We got the hourly ground-based ozone data in Thailand and Malaysia from their department, and one site showing red star in Indonesia from TOR data set. Also, we use ozone profiles from shadows and IAGOS. For the tropospheric ozone, we use OMI product of the monthly TCO in 2 × 2.5 resolution. Then we use GEOS-Chem model to explore the drivers of tropospheric ozone and the surface ozone trend in Southeast Asia region. This, the upper table shows the model description. We use the CDS anthropogenic emissions and the biomass burning emissions from GFAD4 with small fires. Here briefly shows the NOx emissions average over peninsular Southeast Asia and the maritime continent. The NOx emission of biomass burning peaked in March over peninsular Southeast Asia and peaked in September to October over maritime continent, corresponding to the respective local dry seasons. The stable rise in anthropogenic emissions can potentially drive the long-term change of ozone over Southeast Asia. Here we conduct 4 sets of simulations, 1 base simulation and 3 sensitive simulation to derive the drivers of background anthropogenic emissions, Southeast Asia local anthropogenic emissions, biomass burning emissions, and meteorology. First, we show the observed and simulated seasonal surface ozone concentration and trend over Southeast Asia. The surface ozone was high in dry seasons over peninsular Southeast Asia. The ozone maximum is in boreal winter and spring under the influence of northeast monsoon. And over maritime continent, the dry season is between July and October in Indonesia. That shows a higher ozone concentration. And the seasonal cycle of ozone in Malaysia is flat because Malaysia is influenced by both northeast monsoon and southwest monsoon. The right panel shows the MD8 ozone trend from 25 to 2014. Over peninsular Southeast Asia, the surface ozone increased in all seasons with maximum of 1.4 ppb per year in spring. And over peninsular Malaysia, surface ozone also shows significant increase in summer. In the troposphere, the upper panel shows the OMI observed tropospheric ozone trend, which shows that the most significantly ozone increase was over peninsular Southeast Asia in spring, which is about 0.24 DOPS unit per year, and also over maritime continent in spring and autumn, about 0.13 to 0.16 DOPS unit per year. And our model will capture the distribution and magnitude of the tropospheric ozone trend in those 10 years. For the vertical profile, here the gray and black solid line shows the 50th percentile value of shadows and IAGOS data average over 25 to 29 and 2010 to 2014 period. And the green lines are model results. For the one site in Vietnam, we cannot see a significant ozone change during the 2 periods. But in the lower troposphere over maritime continent, the ozone shows a significant increase in spring and fall. Here, I briefly summarize the observed and simulated surface and tropospheric ozone trend. we found varying degree of ozone increase in both post-Near Southeast Asia and the maritime continent region, except that the tropospheric ozone decreased in wintertime over post-Near Southeast Asia, which probably due to the influence of meteorological conditions. Further, I will show the drivers of the surface ozone trend. The upper panel is the surface ozone trend in the base simulation. The other four panels respectively show the contribution from background anthropogenic emissions, Southeast Asia region anthropogenic emissions, biomass burning emissions, and meteorological conditions. The dominant driver for surface ozone trend is the anthropogenic emissions over this region, which contribute about 20% to 54% over post-Near Southeast Asia and 66% to 76% over maritime continent. As for tropospheric ozone, the anthropogenic emissions over Southeast Asia are still a large contributor to ozone increase, but the background anthropogenic emissions and the meteorological conditions plays a more important role, especially for post-Near Southeast Asia. There are 7% to 55% ozone increase due to the background emissions. Here I summarize the main result in our study in those two panels. The black and the red arrow bar shows the ozone trend value in 4 seasons, average over post-Near Southeast Asia and the maritime continent. The bars in different color represent the ozone trend derived by those 4 factors, including background anthropogenic emissions, Southeast Asia anthropogenic emissions, and so on. As I mentioned before, anthropogenic emissions is the main driver for surface ozone trend, and there is a larger contribution from background emissions and meteorological conditions when we consider the tropospheric ozone trend.
30 seconds.
Yeah, I will stop at this slide, show some main conclusion in our study, and thanks for your attention and happy to take your questions.
Shaolin, I have a question from Jin Tai, and he asks, how large are the satellite ozone errors in the mean and in the trends, especially over the maritime continent where tropospheric ozone concentrations are low?
Oh, okay. Can you help me to the slide? You mean this slide? For the tropospheric ozone, I think our model can well reproduce both the concentration and the trend in the maritime continent.
Jin Tai was asking about the size of the errors in the satellite observations.
Oh.
How large are they in both the mean and the trends, especially over the maritime continent?
Satellite ozone error. Here we didn't consider the uncertainty of the satellite observation, but we have corrected the raw anomaly of the OMI data set.
So one to contemplate over and maybe discuss offline with Jin Tai. Falkert asks, where would the background emissions increase come from? Would this be from a source region like the Middle East? And which species would be contributing to this background increase, NOx or methane, or perhaps something else?
I think the background emissions is mainly from the India and China. Because we all know that India and China also experience heavy pollution, and in our result, we can see the panel. We can see the slide 7. I can't move to that. Okay, I won't show the figure, and I think the main background emissions is from the NOx and VOC emissions from India and China, and I don't think the Middle East is important because it's far away from the Southeast Asia.
Thanks, Charlene. Thank you to all of the speakers today. I don't know if there are any logistical announcements that you, Matt, or Paul have. The next session is networking with speakers. So if you have any follow-up questions or perhaps want to clarify anything, please stop by these to meet with the speakers from today's session. Anything else to add, Matt? If not, we'll see you at the afternoon session starting at, well, 2 p.m. British time. Thanks, everyone.
Thank you.